Hello, and in this video we're going to be looking at conservation of momentum. Okay, in particular what we're going to look at in this video are two balls or two spheres colliding into one another. Okay, so to help you illustrate it, I'm just going to play this little video here to help you visualize the scenario. Okay. So that's essentially what we're going to be looking at, right? Two balls sort of colliding into one another. Okay, so we're going to look at collisions and we're going to look at the momentum involved. Okay, so we've seen momentum last time. Momentum basically tells me how fast and how big something is. Okay, so if it's moving fast and it's getting bigger, then it's going to have more momentum. It's going to be harder to slow something down if it has more momentum. So that's the whole idea of momentum. Okay. So, right. So as I just shown you, we've got this situation where we've got these two balls colliding. Let me draw a general sort of diagram for this. So we have particle 1 and particle 2. Okay, ball 1, ball 2. Okay. I'm going to say the first one has mass m1 and the second one has mass m2. Okay, I'm going to be very general with this. And then let's say before the collision, then the first one is moving with a speed of u1, okay, and the second one's moving with u2. Okay, so u1 and u2 are the speeds before they collide. Then they collide. Then let's say afterwards their speeds are v1 and v2. Okay. So those are the speeds afterwards. Okay, so hopefully happy with this sort of diagram. Okay. So there we are. So we expect, obviously, when two things collide, their speeds are going to change. Okay, so those are the speeds before and after. Okay. So what we're going to look at then is the change in momentum before and after. Okay, because their speeds change, you might expect something to change with the momentum. Okay, because remember momentum is velocity times mass. It involves velocity. Where my velocities, my speeds are changing, that might affect momentum. So what we can say is that momentum is actually conserved. Okay, so the total momentum before and after are the same. Okay, the momentum is conserved, meaning total momentum before is equal to the total momentum after. Okay. And that's essentially what we're going to be looking at. Okay, this is what we call the conservation of momentum. Okay. And so we're going to be using that with collisions. Okay. So if I go back to this diagram here, then okay, let me work out all the momentums involved. Okay, I'm going to do that in a different color. Okay, so there's basically 4 different momentums going on. Okay, obviously we've got these two balls, but then they also have 2 different speeds each, so that there's 4 different momentums, if you like. So firstly, I'm going to look at the momentum of the first one before the collision. Okay, so momentum of 1 before. Well, remember, momentum is mass times velocity. So the first one has mass m1, and initially the velocity is u1. So it's going to be M1 U1 there. Okay, hopefully happy with that. Then I'm going to look at this one, so the second one before. Okay, so the momentum of the second ball before. But again, the mass now is M2 and the velocity is U2. So we times them to get the momentum. So it's going to be M2U2. Okay. Then if I look at this velocity here, well, the momentum there, okay, so momentum of the first one afterwards, well, it's going to be the mass M1 times the velocity V1. So it's M1V1, okay. Then lastly, I want to look at the momentum here, okay. So momentum, the second one after. Well, again, it's mass times velocity, so M2V2. So hopefully happy with all these individual momentums for each different velocity, okay? So, what we've looked at here then, these two are the momentums before the collision. So therefore, the total momentum before, it's got to be these two added together, okay? So if I do it a different colour then, what that therefore means is the total momentum before is M1U1 add M2U2. Okay, that's the total momentum before the collision because I'm adding these two together. So hopefully happy with that. And then in the same way, the total momentum afterwards are going to be these two added together. Okay, so it's going to be M1V1 add M2V2. Okay. And so this is the total momentum afterwards. Okay. And so therefore, if this is the momentum before and this is the momentum afterwards, momentum is conserved, so they equal each other. Okay. And so we can use this sort of equation, okay, to help us figure stuff out. Okay, we're going to look at some problems in a second where we're going to be using this conservation of momentum. But hopefully you're happy with how I've got to that. Okay, so hopefully happy with all the momentums, okay, before and after for the particles. But there we are. I'm also going to make a final point, a technical point, that momentum is only conserved when there's no external forces involved, okay? I'll explain what that means in a second. So momentum is only conserved if there's no external forces involved. So what I mean by external forces is forces from external things, okay? So for example, it could be the floor they're on, okay? So you might get friction from the floor. That would be an external force, okay? So friction from the floor, or even air from the wind, air resistance on the wind, okay? Okay, so that's the sort of assumption we make with all these problems, is that there's no external forces, so no friction, no air resistance, nothing that's affected from anything else, okay? So so there we are. Okay, so we've got this question here first. So here we're told particles A and B have masses 2 kg and 3 kg respectively. They're moving with speed 6 meters per second or 1 meter per second respectively in the same direction along a straight line on the smooth horizontal surface. Okay, a bit of waffle there, right? But what we've essentially got is this diagram here. Okay. So we've got these two sort of balls. Technically they're called particles, okay? In mechanics we refer to the objects as particles. That essentially means it has like no air resistance and stuff like that. So again, ensures there's no external forces, so we can apply conservation of momentum. But don't get too bogged down by the details. We've got the essential diagram here. So we need to find this speed v, okay? Right, so we're going to apply conservation of momentum, okay? And we can use this to work out v. So the conservation of momentum, so we need to basically find the momentum before the collision to equal the momentum afterwards, okay? That's what this is saying. The momentum is conserved, right? So momentum before is momentum after. That's essentially what we're looking at. So what are the momentums then? Momentum before, well, these are the velocities before the collision, okay, for the two particles, and then afterwards it's these velocities, okay? If we just focus on the velocities before the collision, then okay, well, for the first one, for A, the mass is 2, okay, and the velocity is 6. So remember, momentum individually is just mass times velocity, right? We looked at that in the first part. So the mass is 2 and the velocity is 6, okay? And so that's the momentum of A. And then for B, the mass is 3 and the velocity is 1. So then we're going to add on 3 times 1 to get the total momentum for both of them. Then we just need to work this out. So 2 times 6 is 12 and 3 times 1 is 3 to get me 15. Okay. Then we're going to look at the velocities afterwards then. Okay. So afterwards. So again, A has mass 2 and afterwards the velocity is 3.5, so it's 2 times 3.5, okay, mass times velocity. Then for B, it's the mass is 3 and the velocity is v, so it's 3 lots of v, okay. So if I simplify this, I'm going to get 7 add 3 lots of v. Okay, I can't do anything, I can't simplify that anymore, but there we are. So hopefully happy with that, hopefully happy with all the momentums and what I've done there, okay. And so therefore, conservation of momentum tells me the momentum before is the momentum afterwards, okay, in total. So therefore we can equate them together. So momentum before, 15, is equal to momentum afterwards, which is 7 add 3v. And now I've got an equation I can solve for v, right? So, 3v, if I subtract 7, I get 8. Okay? Then I can divide by 3. And then I get v to be 8/3 in exact form, or as a decimal, 2.67 meters per second, and that's 2 decimal places. And there we are, that is the value of v, okay. So that's what that is saying, is that the velocity of b afterwards is 2.67 meters per second, okay. That's the velocity of b afterwards, the speed it's going at. And there we are. So hopefully happy with that. That's essentially what you're going to be doing, okay. Hopefully, so I've just broken it down for you step by step there, but that's essentially what we're going to be looking at, looking at all the momentums, okay. Now I've got this question, and I'm not giving a diagram here, So I'm told a particle P of mass 2 kg is moving on a smooth horizontal plane with speed 4. It collides with a second particle Q of mass 1, which is at rest. After the collision, P has speed 2 meters per second and continues to move in the same direction. Find the speed of Q after the collision. Okay, so we are going to again have to apply momentum, but I'm not given a diagram. Always do a diagram, okay? And I do recommend you do a diagram like this, okay? So I'm going to draw my two balls to represent the particles, right? So the particles are P and Q, okay? So I'm going to label it P and Q like that. Then I'm going to label their masses. P has mass 2 and Q has mass 1. So 2 kg for P and 1 kg for Q. Then I'm going to look at their velocities, okay? So what I'm told is P is moving with speed 4. Okay, so it's going to go towards Q with speed 4. Okay, 4 meters per second there. Okay, Q, I'm told Q is at rest. So that means it's not moving. So it has actually 0 speed. So it's 0 meters per second. It's standing still. So hopefully that made sense, right? So P is going towards Q like that, and then they collide. Then afterwards, we are told P has speed 2 and it continues to move in the same direction. So afterwards, it moves in the same direction. So if it's moving forwards before, it's still going to move forwards after. So it's going to look like that, okay? And the speed is 2. Okay, the speed is now 2, so hopefully happy with that. Then then we need to find the speed of Q. Okay, so so Q's going to also go forwards. Okay, that makes sense, right? Because if P's going to bash into Q, Q's going to be pushed forwards. But anyway, I'm going to call that V. Okay, I'm just going to call that speed QV. That's what I want to work out. What is V here? That's what it's asking me to do. Hopefully happy with that. So I'm always going to do this sort of diagram for these questions, okay? So we're going to apply momentum, okay? We're going to apply conservation of momentum. And actually, I can do it all in one go. I don't have to break it down like I did in the first example. So if I look at all the momentums then before, okay, well, for P, the mass is 2 and the velocity is 4. Okay, so it's going to be 2 times 4 for P. Then for Q, before the mass is 1 and the velocity is 0. So it's going to be 1 times 0 for Q. So that's the momentum before, then it equals the momentum afterwards. Now afterwards, well, again, P has mass 2. But then the velocity is now 2 as well. So it's 2 times 2 from P. And then for Q, well, the mass is 1 and the velocity is V. So it's 1 times V. And there we are. So momentum before is equal to momentum afterwards. And now I just need to solve this equation for V. So if I simplify the brackets, I get 2 times 4 is 8. 1 times 0 is 0. So then 2 times 2 is 4. 1 times V is V. So therefore, V add 4 is 8. Then I could just subtract 4 to get V's 4. And there we are. Just like that. Okay, so that's my missing speed for Q. Okay. Then I've got this question here. So here we're told particles A and B have masses 0.5 and 0.2. They're moving with speeds 5 and 2, respectively, in the same direction when they collide. After the collision, A continues to move in the same direction with speed 4. Find the speed of B afterwards. Again, I'm going to do the same sort of diagram. Okay, so I have my two particles here, A and B. Okay, I'm told that they're A and B. A has mass 0.5, so 0.5 kg. B has mass 0.2. And there we are. Then I'm told they are speeds 5 and 2 respectively. So A has speed 5 and B has speed 2, and they're in the same direction. Okay. So they're in the same direction, where it means they're both going to move forwards. Okay? Because they're in the same direction, right? So then A has speed 5 and B has speed 2. Okay, so hopefully happy with that. Okay. Then I'm told that after the collision, A continues to move in the same direction. Okay, so if it continues to move in the same direction, well, again, if A originally is moving forward, it's going to continue to move forward then, right? Because it's going in the same direction. So hopefully that made sense. And the speed is 4. Okay, so there we are. So we then need to find the speed of B. And again, B is going to go forwards. It's going to be pushed forwards. I'm going to call that V. Okay, and that's what I want to work out. I want to find out what this V is. Okay, the speed for B. Okay, so I'm going to apply conservation of momentum once again. Okay, so now, so let's look at the momentums. So before, for A, well, the mass is 0.5 and the velocity is 5. So 0.5 times 5 for A. Then for B, the mass is 0.2 and the velocity is 2. So it's 0.2 times 2. And then that's going to equal the momentums afterwards. Well, afterwards, A has mass 0.5, velocity 4, so it's 0.5 times 4. Then for B, the mass is 0.2, velocity is V, so 0.2 lots of V. Then I just need to simplify this, okay? So 0.5 times 5 is 2.5, 0.2 times 2 is 0.4. Then that equals 0.5 times 4, which is 2. And then 0.2 lots of V. And then I can just solve this for V. Okay. So I get 0.2 V, add 2 to be 2.9. And then 0.2 V, subtract 2, I get 0.9. Then if I divide by 0.2, I get V to be 4.5. Okay, and that is the speed of B afterwards. Okay, so 4.5 there. Okay. Then I've got this question here. So here I'm told a particle P of mass 150 grams is at rest on a smooth horizontal plane. Second particle Q of mass 100 grams is projected along a plane with speed U. Collides directly with P. On impact, the particles join together and move on with speed 4. Find the value of U. Okay, so this question is a bit more interesting, a bit more complex. So again, we're going to draw the diagram as usual. And so I've got P and Q. Now P has mass 150 grams. However, that's not in the standard units. We need that in kilograms. So 150 grams in kilograms is 0.15. Okay, if you divide by 1,000, right, to get it in kg. Likewise, Q has 100 grams, so that's 0.1 kg. So we must convert it into kilograms in our standard units. So 0.15 kg for P and 0.1 kg for Q. So that's the first thing. We're hopefully happy with that. Then I'm told P is at rest initially. So P has 0 speed. Okay, so 0 here. Then Q is projected with speed U. And it collides with P. So what that's saying is Q is going to have to go towards P. So it's going to actually go backwards like that. Okay. And the speed here is U. Okay, so U here. Then I'm told on impact, the particles join together and they move on with speed 4U. Okay, so this is where it gets a bit complicated. So we're told afterwards they actually join together. That actually can happen. The particles, they don't have to bounce off each other. They can actually stick together. For example, it could be like two cars. Okay, think about in a collision, perhaps like in a car crash. The cars basically lock into each other. They like crash into each other. They're not going to separate off. They stick into each other. So it's something like that. Okay. So if they join together and they move with speed 4, they're both going to move together as 1. So they move with the same speed. And they're both going to move to the left. Okay. Because Q is pushing into P to the left. And so they're going to have to move to the left afterwards. Okay. Anyway, so that's 4. Okay, 4 and 4. So hopefully happy with that. So the main idea is that because they join together, well, they're basically like one unit. So they have to have the same speed afterwards, if that makes any sense. But hopefully happy with that. It's quite a weird question, but I thought I'd go over it. Okay. And so then at this point we can apply the same sort of stuff. So conservation of momentum. Okay, so again, for P, the mass is 0.15 and the initial speed is 0. So it's 0.15 times 0. Then for Q, the mass is 0.1 and originally the velocity is u. Then afterwards, that's going to equal 0.15 times 4 for P. So 0.15 times 4. And then for Q, the mass is 0.1. And again, the velocity is 4. Okay. And so now I've got this equation, right? So firstly, 0.15 times 0 is 0. 0.1 lots of u. Then that's going to equal 0.15 times 4, which is 0.6. And then 0.1 times 4 is 0.4. So therefore, 0.1 u is 1. Okay. And then divide by 0.1. So u has to then be 10. Okay. And there we are. That is the value of u. Okay. Now I'm going to be looking at impulse. Okay. So again, remember from the first part of this chapter, we saw that impulse is effectively sort of a pushing effect. Okay. And so what happens is when the two particles collide, they push into one another. So there's impulses and it's going to look like that diagram there. Okay. Now if I break this down, okay, so obviously we've got our two particles, right? Like this. So what's going to happen is the two particles collide, they push into one another. So the first one's going to push like that into the second one. So the second one will get an impulse like that, okay, which matches the impulse here, okay. Likewise, the second one will push into the first one in the opposite way. And so the first one will also get an impulse in the other direction, which represents the impulse there. So that's essentially what's going on, okay. So the two particles, because when they collide, they effectively push into each other. Therefore, there's an impulse involved, because impulse is to do with like pushing and stuff like that, okay. And so we're going to be using this impulse alongside conservation of momentum, okay. But hopefully happy with the diagram here, and it should always look like this, okay. The impulses should look like this, okay. But there we are. And actually the last thing I want to look at is again, directions matter, okay. So what we've seen in the first section is that the direction things are moving in, it does matter, because sometimes things will move in what we call the negative direction, and sometimes things move in the positive direction. So what we're going to say is forward is a positive direction, okay, and then backwards like that is the negative direction, right? Hopefully that made sense, right? You go forward, it's positive, backwards, it's negative, okay? You technically could negate them. You could flip them and you could say backwards is positive, forwards is negative. But it honestly makes so much sense to be able to just treat it, to take this way round, to be positive and negative. But anyway, so what do I mean by this? If I just give a quick example then, let's say I have one particle here. Let's say the impulse of the impulse here. Okay. Then let's say I have some speed, I don't know, 6. Oh. And then afterwards the speed is 3. Let's say the mass is 1, let's say. Okay. Now how can I work out the impulse in this example? Well, I can use the impulse formula, right? So impulse, remember from the first section, impulse is mv take away mu. It's the change in momentum, right? However, I'm going to need to consider the directions of both the impulse and the velocities, okay? So directions matter. So the impulse is acting in the backwards direction. It's acting in the negative direction, right? Impulse is acting backwards. So actually what we need to do is negate the I. So we're going to have minus I. The negative here accounts for the negative direction the impulse is moving in. So then the mass, which is 1 here. Then V's my speed afterwards, which is 3. But again, that's in the negative direction. So we need to do negative 3. The negative accounts for the negative direction of the velocity, okay? Then I'm going to take away mu. So 1 for m, and then u is 6. But this velocity, right, is acting in the positive direction. So actually we can just take it as positive 6. Okay. So hopefully happy with the negatives and the positives here. Okay. So things moving in the negative direction have to be negated like that. And then anything positive is going forwards. Okay. Hopefully happy with that. I think at first people find that a bit tricky to get your head around, but there we are. Okay, technically, by the way, this is because these things are vectors. Okay, hopefully you would have seen that in A level in normal maths already, or maybe even at GCSE. So actually we're dealing with vectors, which are things that basically have direction. Okay, so because these things are vectors, their direction is important. So that's why we have to negate things if they move in the negative way. Anyway, hopefully happy with that. Now I can work out the impulse by just solving a sort of equation, right? So minus I is minus 3, then minus 6. So minus I is minus 9. Then I can just flip the negatives to get positive I is positive 9 in Newton seconds. And so actually that's my impulse, okay, 9. And there we are. So that hopefully that example gives you like a flavour of what I mean by the directions and how we can work out the impulse. Okay, so we've got this question here. So here we're told two particles A and B of masses 2 kg and 4 kg are moving towards each other in opposite directions. Particles collide. Before the collision, the speeds of A and B are 3 and 2. After the collision, the direction of motion of A is reversed and its speed is 2. And then find the speed and direction of B after the collision. Okay. So again, we're going to need to draw a diagram, and it's going to be the same sort of one we've been doing before. So we have our two particles, A and B, like that. A has mass 2 and B has mass 4. There we are. Then what about the velocities? Okay, well, we're told that the particles are moving towards each other in opposite directions. Okay, so that means that A is going to go to B, and A is going to move forward like that, and B is then going to move backwards towards A. And so that's what that's going to look like. So hopefully happy with that. So they're towards each other in opposite directions, because one's forwards, one backwards. The speeds, well, before, A has speed 3 and B has speed 2. So 3 and 2 then. Okay. Hopefully happy with that so far. Then I'm told after the collision, the direction of motion of A is reversed and the speed is 2. So the direction of motion of A is reversed. What does that mean? So the direction of motion tells me, well, what direction you're moving in. effectively. So if the direction of motion is reversed, A originally is moving forwards. So if we reverse that, it's then going to go backwards afterwards. And hopefully happy with that then. And the speed now is 2. And there we are. Okay, then I need to find the speed and direction of B. So we're not really told where B can move. B could move forwards, or it actually could move backwards. We're not actually given any information about where it could go. We don't need the information because what will happen is if we get a negative answer, it turns out we can just flip the direction. But anyway, if we don't know any directions, we can just assume we go forwards, okay? It just makes our life easier, okay? Because it's positive directions. We don't need to do anything extra. Let's just assume B goes forwards then. Then I'm going to call that speed V. Okay, so hopefully happy with the diagram, okay? So at this point, I'm going to apply, well, conservation of momentum, right? Okay, so momentum, what we've been doing previously. So for A, well, the speed, the mass is 2 and the velocity here is 3. So it's 2 times 3. And then for B, the mass is 4 and the velocity is 2. However, what I said was directions matter, right? And that also applies to the velocities, okay? Now, as I said, I'll do it here. Forward is positive and backward is negative, okay? But what do you see is that this velocity is going backwards. It's in the negative direction. So actually, we're not going to do 2. We're going to do minus 2, okay? So it's going to be times by minus 2 because the minus will account for the negative direction, okay? That's very important, okay? So we do need to pay attention to the direction and any negatives, okay? Hopefully happy with that. Then afterwards, A has mass 2 and velocity 2, but that's also going in the negative direction. So it's going to be 2 lots of minus 2, okay? And then for B, the mass is 4 and it's V, but that's going in the forwards direction. It's positive, okay? So it's just 4 times V, like that, okay? And then if we simplify this, okay? We get 2 times 3 is 6. 4 times minus 2 is minus 8. Then that's 2 times minus 2 is minus 4. And then 4 lots of V. So therefore 4V minus 4 is going to be minus 2. Then if we add 4 to both sides, we get 4V is 2. Then V divided by 4. You get 0.5. Okay. And there we are. That is the speed V there. Okay. The 0.5 there. So that is my missing speed then, 0.5. But actually they didn't want me to just work at the speed. They wanted me to work at the direction it's moving in. Okay. Now, obviously it looks like it's going forwards, right? But actually we need to be more specific. We can't say it's going forwards. Okay. I'll go into that in a little bit. But what we need to do to describe the direction, we need to use comparative language, okay? So either we can compare to the direction before. So B's originally going backwards and now it's going forwards. So if we describe that comparatively, we can say the direction is reversed or it's changed direction, okay? So we could describe the motion as, or describe the direction, we could say the direction is reversed, okay? So it's comparing it to its original direction, okay? Or instead of comparing it to what it was before, you could compare it to this other particle. So if B is going forwards but A is going backwards, we could also compare it and say B is moving in the opposite direction to A, okay? Or we could say the direction is opposite to A. okay? And either of those should be fine, okay? So you need to use comparative language. You need to compare it to something else. So compare it to the direction before or the direction of the other particle, okay? Now, why can't I just say it's going forwards, okay? Because what the diagram I've drawn is just how I see the situation. What actually could happen is everything could flip, okay? So actually B and A could swap places effectively. So actually B could be on the left and A could be on the right, okay? And so if everything flips, okay, B's then going to go towards A with speed 2 and A is going to go towards B with speed 3, sorry, like that. And then afterwards, A is going to go like that with speed 2. And then B is going to then flip the other way around of 0.5, okay? So actually, there are two different ways you can actually interpret or draw the diagram, okay? Both of these are valid, the exact same sort of thing. But you can see everything's flipped, okay? Hopefully you can see with this diagram, it's completely flipped to the diagram we've done, okay? And both of them are valid, okay? It's just how we see the situation. But hopefully you can see then for B, the direction is actually in the opposite way. Okay, it's not going forwards anymore, it's going backwards. So we can't just say it's going forwards or backwards because the situation could be completely different to how we see it, okay? So that's why we need to use comparative language, okay? Because it might be a completely different situation and things flip, okay? So we can't say it's going forwards because it might not be. It might be this situation where it's actually going backwards, depending on how we see the situation. So we need to use comparative language. So that's very, very important when you're describing directions things are moving in. Okay, I just want to drill that in, but there we are. Okay. Anyway, then part B is asking now for the impulse. Okay, so the impulse given by A to B. Okay, now let's just ignore that little bit for a second. Where's the impulse going to act? Well, it's going to be like this diagram we've looked at here, right? It's going to be the exact same sort of thing. That's where the impulses are going to act, okay? So, if I label my impulses, well, A is going to push into B like that. So B is going to get an impulse here. Likewise, when they collide, B is going to push into A like that. So A is going to get an impulse here. And so there we are. And actually, the impulses are equal, okay? Both A and B have the same impulses, but obviously in just opposite directions. So actually, I could consider either diagram, okay? But they want me to consider the impulse of A to B. So the impulse that A gives to B. So the impulse of B then, right? The impulse that B gets. So let me just consider the diagram for B on its own, okay? So I can work out the impulse by just considering B. So I'm just going to draw the diagram for B below. Okay, so this is the diagram for B then. I've just copied the diagram out here. So if I want to work out the impulse, well, I can use the formula, okay? Impulse is change in momentum. So I is mv take away mu, okay? That's the formula I want to be using. So in this case then, again, directions matter, but the impulse is going forwards in the positive direction. So it's going to be positive I is going to be the mass, which is 4, lots of V, which is going forwards. So it's going to be plus 0.5. Okay, so positive 0.5. Take away M, which is 4, lots of U, which is 2. But U, the initial velocity 2, here is going backwards. So we actually need to negate and do minus 2. Okay, so therefore we get I to be 4 times 0.5, which is 2. And then minus 4 times minus 2, that's a double negative. Okay, we've got a double negative here. So minus 4 times minus 2 is plus 8. So therefore the impulse is 10. Okay, and there we are. And you know you've done it right if your diagram makes sense, because you shouldn't get any like dodgy negatives, okay? You should get a positive answer here, okay? So you should know that that's how you've done it right. But anyway, there we are. The impulse is 10. And there we are. Now, as I said, the impulses are equal. Okay, so A and B, and it will always be the case that these two particles have the same impulses. So actually, I could have just did A instead. So I'm going to now do the same sort of question, but for A. So I'm going to draw the diagram for A out. Okay, so this is the diagram for A. So if I work out the impulse this way then, with A instead of B, again I'm going to use the same formula. I is mv take away mu. So in this case, the impulse, which is now in the negative direction, so it's going to be minus I to account for the negative direction. It's going to be the mass, which is 2 lots of V. Now the V is 2, but again that's also in the negative direction, so it's going to be minus 2. Then minus 2 for m lots of u, which is 3, but that's in the positive direction, so it's going to be plus 3. Okay, so hopefully happy with the negatives there. Okay, then I can just solve and simplify this equation. So minus I is 2 times minus 2, which is minus 4. Minus 2 times 3 is minus 6. So therefore minus I is minus 10. So then cancel the negative to get I positive 10. And there we are. So it's almost like magic that the impulses are equal. Okay, impulse is 10 for both of them. Okay, and so there we are. So 10 for impulse overall. Okay, and so it actually doesn't matter which particle you find the impulse for, because the impulse will be the same either way. Okay. Then we've got this question here. So we're told two particles A and B of masses 2 and 4 are moving towards each other in opposite directions. Before the collision, the speeds of A and B are 3 and 2. Given that the magnitude of the impulse is 7, find the velocity of A and B after the collision. Okay. So again, I'm going to draw a diagram, right? So we have A and B like this. A, B. A has mass 2 and B has mass 4, like that. Okay, what about the velocity then? Well, we're told before they're moving towards each other in opposite directions. So A is going to have to go to B, like that, and B is going to have to go to A, like that, in the other way. And there we are. Okay, then the speeds, well, before A has speed 3 and B has speed 2. Okay, so hopefully you're happy with that. Okay, then what about afterwards? I'm not told about anything afterwards. Okay, I need to work out the velocity afterwards. Now again, I'm not told any direction things are moving in, so let's just assume they both move forwards afterwards. Okay, let's just assume that. So I'm going to call the velocities V1 and V2. Okay, so hopefully happy with that. So that's what I want to work out. I want to work out V1 and V2. Now, I'm also told information about the impulses. The impulse is 7. Okay, so remember the impulse, so A is going to push into B, like that, forwards. So B will get an impulse forwards. But the impulse is 7, right? 7 Newton seconds. Likewise, B is going to push into A in the opposite direction, so A is going to get an impulse here, but again the impulse is 7. And there we are. So actually, if I want to work out V1 and V2, I don't even need to use momentum here. I can just consider the impulses, okay? Because again, the impulses are equal onto one another. So if I just consider A firstly, again, I can use the impulse formula. Impulse is mv take away mu. So for A, well, the impulse is 7, okay? But that's going in the negative direction. So it's actually going to have to be minus 7. The negative to account for the negative direction. So minus 7 is mv take away mu. The mass is 2. V is V1, going forwards. Take away 2 lots of u, which is 3, which is also going forwards, so that's positive. And there we are. So we can solve this equation, right? So therefore we get minus 7 to be 2v1, take away 6. So 2v1, add 6, I get minus 1. So V1 is going to be divided by 2 to get minus 0.5. And there we are. And so I have negative 0.5, right? I have a negative answer. So minus 0.5 here. Okay. So again, the negative. Now remember, remember we just assumed it was going forwards, right? We don't actually know for sure where things are moving in. I just assumed it went forwards, but actually my answer is negative, right? It's a velocity, so the direction matters. So because it's negative, what that's telling me is that the true direction is opposite. So if I'm saying we're going forwards, then actually I need to flip the direction. Okay, and then it becomes positive 0.5, which is what I want. Okay, so that's actually telling me the true direction is actually moving in is backwards. Okay, so actually the sign of my answer will tell me what direction it's moving in. Okay, so hopefully happy with that. So it's actually moving backwards. Okay, not forwards. Then I can find V2. So now I'm going to consider B. Okay, by using impulse. Okay, so again the impulse is 7, that's positive 7 because it's positive direction forwards. Then it's going to be mass times V, which is V2, and then take away mu, so mass is 4 and u is 2, but that 2 is going in the negative direction, so it's minus 2 actually. So then we get 7 to be 4v2, take minus 4 times minus 2 is plus 8, okay, double negative. Then I can solve this for v2, so 4v2, subtract 8, I'll get minus 1. So v2 divided by 4, I get minus 0.25. And once again, I have a negative answer, okay, so v2 is minus 0.5, and 0.25, sorry. So again, what does that tell me? My answer is negative. My velocity is negative. So I need to reverse the direction. And so the true direction is actually, it's telling me it's going backwards. Okay. And so then it becomes positive. Okay. So actually it turns out none of them are moving forwards. They're actually both going to move backwards afterwards. Okay. So there we are. And so lastly then, we can actually define the velocity then, because velocity is speed and direction. Okay, so it's speed in a particular direction. So if we want to write down the velocities of them, well, what are their speeds and directions afterwards? So if I firstly look at A, okay, well the speed is 0.5 and it's going backwards as we discussed, right? So if I do it here then for A. The speed is 0.5 meters per second. Then the direction, okay, because that also matters, okay. Well, again, I can't say it's going backwards. I can't use language like that. I need to use comparative language. So if I compare it to what it was before, it's going forwards and then it's going backwards. So if I compare, I can say that its direction is reversed. It's going in the opposite direction it once was. Okay, so I can say that the direction afterwards is reversed. And there we are. So that's my velocity, right? So velocity is speed and direction. Then for B, the speed, well, if I look at B afterwards, well, the speed is 0.25 meters per second. And then the direction it's going in, well, again, it's going backwards, but I don't want to say that. I want to use comparative language to be more accurate. But it's also going backwards before. So if I compare it, I can say the direction is unchanged. Okay, before and after. So the direction afterwards is unchanged for B. And there we are. So there we are. So whenever you're describing direction or something like this, you must use comparative language. Okay. Okay, then I've got this question here. So two particles P and Q of masses 3 and 2 are moving along the same line. Then they collide. After the collision, both the particles are moving in the same direction. The speed of P is 1 and the speed of Q is 1.5. The magnitude of the impulse is 9 Newton seconds. So we need to find the speed and direction of both of them before the collision. Okay. So again, let's not get too bogged down. So we're going to just draw the usual diagram. Okay. So we have P and Q. The masses are 3 and 2. 3 kg and 2 kg, right? Yeah. Right, so then what about our velocities? Now actually we don't know what the velocities are before the collision. That's what we want to work out, what the speeds are before. But what we are told is that afterwards they're moving in the same direction. That's afterwards. So let's say they're both moving forwards. Okay. Okay, again, if you don't know the direction, just assume it's going forwards. Okay, it makes your life easier that way. The speed of P is 1, so 1 here, and Q has speed 1.5 afterwards. So there we are. So those are my velocities afterwards. Okay, so before then, let's say they're both moving forwards. Okay, I'm going to call P and Q. I'm going to call the speeds U1 and U2. Okay, so I want to find U1 and U2. But actually what I am also told is what the impulses are. Okay, so the impulses are 9 Newton seconds. So remember, P is going to push into Q, so Q is going to have an impulse here. The impulse is 9. Okay. Likewise, Q is going to push into P, so P is going to get an impulse here. Which is also going to be 9, right? So actually, I don't even need to use conservation of momentum because I can just use the impulses instead for both of them, right? So if I just look at P firstly, if I just look at the diagram for P, okay, well, again, remember impulse is mv take away mu. So in the case of P, the impulse is 9, but it's going to be minus 9 because it's in the negative direction, right? The minus 9 is going to be the mass 3 lots of v. So mv, which is 3 times the 1 here. Take away 3 lots of u. So u here is u1, okay? So hopefully happy with that. And now I can solve for u1. Okay, so the initial speed for P. So therefore minus 9 is going to be 3, take away 3 u1. Then I can solve for u1. So minus 3 u1, subtract 3 to both sides, I get minus 12. Therefore u1, if I divide by minus 3, I get positive 4. Okay, and there we are. So u1 is 4. And there we are. Then for Q, okay, now if I consider Q on its own, okay, I can consider the impulse here as well. So again, I'm going to use the impulse formula. So the impulse is 9, that's forwards, so it's positive 9, because it's in the positive direction, right? So it's going to be mv take away mu, so m is 2, v is 1.5 going forwards, take away 2 lots of u, which is u2 here. And there we are. And so then I just solve this equation for u2. So therefore 9, 2 times 1.5 is 3, take away 2 lots of u2, therefore minus 2 lots of u2. If I subtract 3, I get 6. Okay. Therefore, if I divide by minus 2, so 6 divided by minus 2, that gets me u2 to be minus 3. Okay. And there we are. u2 is minus 3. Okay, so we've got an answer of minus 3. So if we've got a negative speed, that tells me I need to flip the direction. I'm going in the wrong direction is what I'm saying. So whenever we get a negative velocity like this, we need to, what that's telling me is I need to flip and reverse the direction. Then it would become positive. Okay, so what that is telling me, I'm actually going sort of backwards. Okay, And so there we are. So the sign of my answer, okay, the sign of my answer tells me the direction I'm going in. Okay, so hopefully that made sense. Right, so now I need to describe the speed and direction of both of them before the collision, right? So firstly, for P, the speed is, well, what's the speed before the collision? It's 4, right? It's 4. So it's 4 meters per second. And the direction, now, remember, when I describe direction, I need to use comparative language. So P is going forward and it's still going forwards afterwards. So the direction is unchanged. So that's what I can say. So the direction is unchanged compared to afterwards. Okay, and there we are. Okay, remember, I can't say it's going forwards. Okay, I can't say it's going forwards because, like in the last example, everything could be flipped. Then for Q, where we can see the speed is 3, okay. Okay, then what about the direction? Okay, well, we can see it's going backwards here, but then if we compare it then to afterwards, it's actually going forwards, so there's a change in direction. So we can say the direction of motion is opposite compared to afterwards, right? So the direction is opposite compared to afterwards. And there we are. Okay, now we're going to be looking at some harder problems where there's some algebra thrown into it now. Okay, now the questions look scary, right? For example, this question here, we've got m's and stuff like that. But it's going to be the exact same process, right? We're going to use conservation of momentum, and then maybe impulse, right? That we've seen previously. The exact same stuff, right? So please don't be put off by the questions, okay? But let's have a look at this one. So we're told a particle A of mass 4m is moving along a smooth horizontal surface with speed 2u. It collides with another particle B of mass 3m on the moving with the same speed on the same line in opposite direction. Given that A is brought to rest by the collision, find the velocity of B after the collision. So again, the first step is we're just going to draw the diagram, right, of our two particles. So we have A and we have B, right? A has mass 4m and B has a mass 3m. Okay, again, don't be put off by the m's and all the letters, right? It's the exact same sort of idea. Then as for the velocities, before, we're told they are moving in the opposite direction towards each other, right? So A is going to have to go towards B and B is going to have to go towards A like that. Okay, so they're in the opposite directions like that. As for the speeds, A has speed 2u, so 2 lots of u there. I'm also told B has the same speed, so B also has speed 2u. Okay, so hopefully happy with that. Then I'm told A is brought to rest by the collision, so afterwards A goes to 0 speed, like that. Okay, so then I need to find the velocity of B afterwards. Again, I don't know where B is going to go. I'm going to, well, I'm pretty sure B will have to go forwards, but let's just say it goes forwards, right? Okay, I'm going to call that speed V. Okay, so I want to find V there. Okay, so I'm going to apply conservation of momentum. So, okay, for A, the mass is 4m and the initial velocity is 2u. So 4m lots of 2u, hopefully happy with that. Then for B, the mass is 3m, lots of the velocity 2u, but that is going in the negative direction. Okay, it's going in the negative direction, so we need to do minus 2u. Okay. Then afterwards, A has mass 4m and velocity 0, so 4m lots of 0. and then 3m lots of v for b there. And there we are. Hopefully happy with that. Okay. So those are just all the momentums before and after. Then we can simplify the equation. So 4m times 2u is 8mu. 3m times minus 2u is minus 6mu. That's going to equal 4m times 0 is 0. 3mv. Okay. I can actually then tidy this up. I can collect the mu's. 8 lots of mu take away 6 lots of mu is 2 lots of mu, right? And that's 3mv. Now what we can then do is I can divide by m. I can cancel the m's out. Okay. So then I get 2u is 3v. And so therefore I can get v then, right? So v, if I divide by 3, is 2 over 3 lots of u. And there we are. Okay, now that's not a number. Okay, that's not a physical number like we used to. But that's still fine. Okay, that's still my answer. Okay, it's just in terms of u. But actually that is my answer for v. Okay, so 2/3 u. And so there we are. That is the velocity of b. Okay. And there we are. And so yeah, so it's a very common thing that we need to leave our answer in terms of u. Okay. But there we are. Then for part B, he wants me to find the impulse given by A to B. So the impulses now. Now again, the impulses are going to look like this. So A is going to push into B forward. So B will get an impulse forwards. Then B will push into A. So A will also get an impulse like that. Okay. It doesn't really matter, to be honest, which particle I consider to find the impulse. Okay. But the question says the impulse given by A to B. So that's the impulse given to B. Okay. So you could consider B. Okay. If you wanted to, if you were to do that. Okay. If I was to copy the diagram out for B. Okay. So this is my diagram for B. I've just copied it. Okay. So I want to find the impulse then. So again, I'm going to use the formula I is mv take away mu. So in this case, the impulse, which is positive because it's going forwards, it's going to be m. Now the mass is 3m, so it's 3m, and then v is 2/3 u. Okay, which is also positive. Okay, then I'm going to take away 3m lots of u, which u, by the way, is the initial speed. So u here is 2u, and that's going backwards. So actually, I need to do minus 2u. Okay. And so now I can solve this equation for I. So I, well, 3m times 2/3 u, that's going to be 2mu. Okay, then minus 3m times minus 2u, that'd be plus 6mu. Then I can add the mu's to get 8 lots of mu. And there we are. That is my impulse. Okay. Again, that's the best I can do. Okay, it's not an actual number, but that's my expression for the impulse. Okay, so 8 mu Newton seconds, and there we are. Then I've got this question here. So here we're told two particles P and Q of masses m and km moving towards each other in opposite directions. Particles collide. Before the collision, the speeds of P and Q are 3u and u. After the collision, the direction of motion is reversed for both of them and the speed is halved. And so then I need to find K. Okay, so again, the same strategy is, as always, I'm going to do my diagram first. So I've got this collision between P and Q. The masses are M and Km. So M and Km. Okay. And we're told that they're moving towards each other in opposite directions. So P is going to go to Q like that and Q to P in the other way like that. Then I'm told before then the speed, well, P has speed 3u and Q has speed u. Okay, and there we are. Hopefully happy with that. Then I'm told after the collision, the direction of motion of both of them is reversed. So the direction they're going in for both of them is reversed. So P originally is going forward. So then it's going to reverse and go backwards instead. Likewise, Q is originally going backwards, so then it's going to go forwards instead. Okay. I'm also told the speed of each particle is halved. So originally the speed is 3u for P, so it's going to be 3 over 2u afterwards. Likewise, originally the speed is u, so it's going to go to a half u afterwards. Hopefully happy with that. Okay. So then, well, I can do conservation of momentum. Okay, it's the only thing I really can do here. So I might be able to find K that way. So for P, the mass is m, and initially the velocity is 3u, so m lots of 3u. Then for Q, the mass is km, and the velocity is u, but that is going negative, is in the negative direction backwards, so we need to do negative u. Okay, then afterwards, it's going to be m lots of 3 over 2. It's going to be m lots of 3 over 2u, but that's also going in the negative direction backwards, so it's minus 3 over 2u instead. Okay, and then it's km, and then a half u like that. And there we are. So that's my momentum. Okay. Then I can just simplify this equation. So m lots of 3u is 3mu minus kmu is minus 3 over 2 mu and a half kmu. Hopefully happy with that. Okay. Then I can move stuff. Okay, so I have 3mu add 3 over 2mu is kmu add a half kmu. So get all the k's to one side, right? So then I can collect the terms. So 3 lots of mu and 3 over 2 lots of mu is 9 over 2 lots of mu. Is then if I then k lots of mu and a half k lots of mu is 3 over 2 k lots of mu. Okay, so hopefully with me here. So again, hopefully happy with the algebra here. So then I can actually cancel the mu's on both sides. I can cancel the mu's, divide by the mu. To get 9 over 2 is just 3 over 2k. And so then we can solve quite nicely for k, right? So if I divide by 3 over 2, so 9 over 2 divided by 3 over 2 to get me k. If I do that, I get 3. And there we are. K is 3 there. Right. So then in part B, it wants me to find in terms of m and u, effectively the impulse. Okay, it wants me to find the impulse. So again, the impulses are going to be like that. So Q has an impulse forwards and P has an impulse backwards. Okay, the exact same way we've been doing it so far. So again, I can consider either diagram, either particle, right? Now it wants me to find the impulse by P to Q. So the impulse given to Q, right? But again, it doesn't matter. The impulses are the same. So let's just say I consider P instead. Okay. I don't have to do Q. Okay. I'll get the same answer anyway. So if I consider P then, so I have the impulse, but that impulse is going in the negative direction. So it's minus I. It's going to be mv take away mu. The mass is m. Lots of v. So the velocity afterwards is 3 over 2u, but that's also going negative direction. So it's going to be minus 3 over 2u. Take away m lots of u now, the initial speed, which is 3u. Okay. So hopefully happy with that. So all I've done here was, again, the impulse is mv take away mu. Okay, so hopefully happy with that. And hopefully happy with the negatives, okay, in the negative direction and so on. So now I can simplify this. So minus I is going to be minus 3 over 2 mu, take away 3 mu. Then I can collect the terms. So minus 3 over 2 lots of mu, take away 3 lots of mu is minus 9 over 2 lots of mu. And then I can just get rid of the negatives to get positive I is 9 over 2 mu. And that is my expression for the impulse. Okay, 9/2 mu there. And actually, if you was to do Q, instead, the impulse should also be 9/2 mu. Okay, the impulses will always be the same no matter what. But that's my impulse. Okay, so hopefully happy with that. Okay, so we're going to look at some exam questions then. So we've got this one first. So we've got two particles P and Q of masses 3m and 2m moving on the same horizontal plane. They're moving in opposite directions when they collide. Before the collision, P is moving with speed 2u, and the impulse exerted is 9mu/2. So find the speed of P afterwards. Again, I'm going to do a diagram, okay? So first of all, do a diagram. So we have P and Q. Now P has mass 3m and Q has mass 2m, like that. Then I'm also told they're moving in opposite directions. Okay, so that has to mean P is going to go to Q like that, and then Q to P in the other way. So they're in opposite directions. Then I'm told before the collision, P has speed 2u. Okay, I'm actually not told anything about Q, but that actually doesn't matter. Because it's all about P. Because I'm told that the impulse is 9mu/2. So P will get an impulse backwards of 9mu/2. And so it wants me to find the speed of P afterwards. So let's say P goes forwards afterwards. So I just need to work out V. So actually, so to work out V, the speed of P afterwards, I can just use the impulse for P. So I don't actually care anything to do with Q, really. So for P then, the impulse is mv take away mu. So in this case, the impulse, which is 9mu/2, but that's in the negative direction. So I need to negate that, okay? So minus 9/2 mu, which is my impulse, okay? The mass is 3m, so 3m lots of v, okay? Take away 3m lots of u, which is the initial velocity 2u. So hopefully happy with that. Then I can solve for v, right? So that means minus 9/2 mu is 3mv. Take away 3m times 2u is 6mu. Then I can say 3mv. If I add 6mu to both sides, I get minus 9/2 mu, add 6mu. Then I can collect the mu terms. So minus 9/2 lots of mu plus 6 lots of mu is 3/2 lots of mu. And there we are. Then I can get rid of the m's. Okay, I can cancel the m's out. To get 3v is 3/2u. Then I can get v on its own, right? If I divide by 3, I get v to be, so 3/2 divided by 3, I get a half, so a half u. And that is my speed afterwards, okay? Again, it's not a number, it's not a number per se, it's in terms of u, but that is my expression for the speed, okay? And so there we are. Right, so then I've got this final exam question here. I think this one's fairly tricky, actually, but let's have a look. So we've got a particle A of mass 3m and B of mass m moving along the same straight line. The particles move in opposite directions towards each other when they collide. Before the collision, the speed of A is ku and the speed of B is u. After the collision, the speed of A is v and the speed of B is 2v, and the impulse received by B is 3/2 mu. So then part A, we need to find v in terms of u only. Okay, well, before we worry about all of that, let me just draw a diagram. So we have our two particles. We have A and B. A has mass 3m and B has mass m, like that. Okay. Then I'm also told they're moving in opposite directions towards each other, right? So A is going to go to P, and then B in the opposite way is going to go towards A, like that. As for the speeds, before A has speed ku and B has speed u. Okay, So hopefully with me so far. Again, it looks horrible, right? But once you break it down, it's the same sort of stuff. Okay. Then I'm told after the collision, the speed of A is V and the speed of B is 2V. Now, I'm not told what direction things are moving in. Let's just assume they're both moving forwards afterwards. Okay. So then A has speed V and B has speed 2V, like that. Okay. I'm also told the impulse. So the impulse received by B is 3/2 mu. So the impulse for B, so the impulse is going to act like that, because obviously A is going to push into B, so B will get an impulse forwards. That's 3/2 mu, okay, Newton seconds, and there we are. So firstly, I need to find V in terms of U only. Now actually, we're a bit spoilt for choice. You could consider conservation of momentum, but we can't really do that because it wants me to find V in terms of U only. If I was to use conservation of momentum, I'd need to involve K. That speed there, right? But actually, they told me the impulse for B. And actually, what I can then alternatively do is consider the impulse for B only. Okay, then I can get an expression that way. So I'm going to consider the impulse for B, right? So again, I is mv take away mu. So in this case, the impulse, which is 3/2 mu, which is positive because it's in the positive direction forwards. So the mass m lots of v, which is 2v here, take away m lots of u. Now the initial velocity is u, but going backwards, so actually we need to negate that to be minus u. Hopefully happy with that. Then I can simplify. So 3/2 mu is 2mv. Then plus mu, right? We've got double negative. Then if I move, then I just have 2mv, move the mu to the left, so we have 3/2 mu, take away mu. So then we can add the mu's. So 3/2 lots of mu, take away 1 lots of mu is a half lots of mu. Okay. Then I can get rid of the m's. Okay. Divide by the m, cancel it out to get 2v to be a half u. Then lastly, I can divide by 2 to just get v. Okay. The v is just going to be half divided by 2 is a quarter u. And there we are. That is my expression for v. Okay. So v is a quarter u. And there we are. That is v in terms of u only. That's part A done. Okay. And actually, then I can add that on. So v was a quarter u. So v is a quarter u. And 2v then, 2 lots of a quarter is a half. So we get a half u there. So we can add that on. Right, so hopefully happy with me. Hopefully happy with that so far. Okay, so I've just used the impulse for B there. And so part B then wants me to find 2 possible values of K. Now, I think this is where the tricky part of the question comes in. Because what on earth does it mean by 2 possible values of K? Right, well, if we want to find K then, well, now we could use conservation of momentum, right? So conservation of momentum. Okay. So now, so A has mass 3m, initial velocity ku, so it's 3m lots of ku. And then for B, it's mass m lots of u, but that's going negative. Okay, negative direction backwards. So m lots of minus u. And then afterwards then, we get 3m lots of the velocity a quarter u, right? So 3m lots of a quarter u. And then m lots of a half u. Okay. And so I can then I've got this equation, right? So if I simplify, I get 3 kmu minus mu is 3m times a quarter u is 3 over 4 lots of mu, add a half mu. Then, therefore, 3kmu is mu, add 3 over 4 mu, add a half mu. Then I can collect all the mu terms on the right. So 1 lots of mu, add 3 over 4 lots of mu, add a half lots of mu is 9 over 4 lots of mu. And so that's 3kmu. Then I can get rid of the mu terms on both sides. Cancel the mu's out. To get 3k is just 9 over 4. And so now I've got a nice equation for k, right? So if I divide by 3, 9 over 4 divided by 3, I get k. And that's going to be 3/4. Okay, and there we are. But hang on, the question has asked me to find 2 values of k. I've only got 1 here. Right? So, what's that about? So, if you actually look at the question again, remember, I'm not actually told anywhere where A or B move after the collision. Okay? So, if you remember, I said that they both move forwards. But that's only an assumption I made. I don't know for sure they're both moving forwards. I don't know that for sure because the question hasn't told me, right? So, the other case is they don't have to both move forward. The other possibility is that A can move backwards, okay? Now, B can also move backwards. I'm not going to go into it in too much detail here. We look at this more in chapter 4. We look at collisions in more detail. But the idea is A and B can't move backwards, because if you look at the speeds, A is slower than B, okay, because a quarter is less than a half, right? So A is moving slower than B, so B would have to overtake A, because B is moving faster than A, and A is to the left of B. But what we're saying is, if A and B are colliding, okay, if B is going to overtake A, B is going to have to sort of phase through A. B is going to have to sort of pass through A. In sort of weird physics thing, right? You can't pass through particles, okay? So this event cannot happen, okay? B cannot ever pass through A, okay? Because B is faster than A. So anyway, so B will have to go forwards, okay? But A could go backwards, okay? Again, I'm not. We look at that more in chapter 4, okay? But that's one of the so this is the other possibility, okay? So, in this case, then we can apply conservation of momentum when we instead consider this version where A moves backwards instead, okay? So there we are. So I'm going to say or. In the second case, then, if A moves the other way, okay, instead, so if A moves backwards instead of forwards, again, it's the same sort of idea. So if for the conservation momentum is 3m lots of ku for A, and then for B, it's m lots of minus u because that's going in the negative direction. So m lots of minus u. That's going to be 3m. That's going to be 3m lots of minus a quarter u because now it's going backwards, right, in the negative direction. And then for B, it's going to be m lots of a half u, okay? And so now we can solve this equation. So we get 3kmu minus mu is minus 3 over 4 mu, add a half mu. Therefore, 3kmu on the left is mu, take away 3 over 4 mu, add a half mu. And so then if we collect all the MUs here, we have 1 lots of MU, take away 3 over 4 lots of MU, add a half lots of MU. That gets me 3 over 4 lots of MU, okay? And so that's 3k MU. Then I can cancel the MUs to both sides. So therefore I get 3k on its own to be 3 over 4. And so I'm going to solve this equation. So divide by 3, so 3 over 4 divided by 3, I get k to be a quarter, okay? And so that's my other number for k, okay? So either k is 3 over 4 or k is 1 over 4, 1 over 4 there, okay? And that arises because of the two possibilities to where the directions go, okay? So in summary, A could either move backwards or it could move forwards, okay? That's the possibilities that could happen, okay? And so there we are. But quite tricky that is to realise. Quite tricky that is. But there we are. And so yeah, so hopefully happy with that. And again, hopefully you're happy with the algebra, okay? Again, hopefully you're not put off by the M's and the U's and the V's. Hopefully you realise it's the same sort of process, right? Things look ugly, but when you get down to it, it's the same sort of process we've been doing earlier on. But there we are. So that's it for now. I'll see you next time.